On to part 3 now of the Lorentz transformation. Let's remind ourselves where we were. Again, the goal here, I brought the props, remember these, Alice and Bob here, so Alice with her lattice of clocks and measuring system, Bob with his lattice of clocks and measuring system. In our example, we set up where we were assuming Alice was stationary, Bob was moving to the right with respect to Alice, but of course from Bob's perspective, his frame of reference, he's stationary and Alice is moving to the left. And so the idea here is that if Bob measures some event, maybe out here that occurs on what clock 1, 2, 3, 4, 5, something like that, and on some time in his synchronized lattice of clocks, what is that going to be on Alice's frame of reference? What time and location with respect to her lattice of clocks? So that's the idea here. That's what we're after, to make our life simpler. If we can get a nice formula for this, and it'll also give us some more insights into how the special theory of relativity works. So we'd gone through a couple steps and had got into this form right here for our formulas involving xb and t sub b. In other words, the x location of event and the time of the event according to Bob's clocks and his measuring system. And then we'll get t sub a, the time for Alice, and x sub a, the location for Alice. And we'd found out that we got sort of the second terms here, but we still need to find out what g and m are. And so now this is where the algebra really comes in. This video clip may be when we have the most algebra, but we'll take it step by step. We'll try to get the big picture as well. For those of you who like to do a little algebra, you can stop at a certain point and then try to work your way through it, see if you can get the same answer we get at the end, hopefully the correct answer. But here's what we're going to do. We're going to go back to the invariant interval equation. This is one of the big reasons why we derived it a little while back. So remind ourselves what it is. It's c squared for any two frames of reference. This quantity is invariant between those frames of reference. So given t sub b and x sub b, plug those numbers in here. And if another frame of reference, Alice in this case, if the difference between the frames of reference, if they're both inertial and there's some velocity v between them, then c squared ta squared minus xa squared will always be equal to the values with Bob's values put in there. So look at what we've got here. We've got these formulas over here. I want to find out what m and g are. And what would happen if I just took my value for t sub a there, my formula, and plugged it in right here, and took the value for x sub a and plugged it in right here. Because then what would happen is I'd have xb's and tb's on both sides. The xa's would disappear. And ideally then, I'd also have, well, not ideally I would have them, I would have g and m in there, and ideally I'd be able to work it down and figure out what g and m are. So let's try that and see where we go with this. So we're going to have a lot of room here. We'll start over here. So I'm going to have c squared. And what's ta? Ta is gxb. So gxb plus gamma tb all squared. Okay, so I plug that in there. C squared ta squared minus xa squared. And so xa squared is mxb plus gamma v tb squared, okay, equals, just this side stays the same, c squared tb squared minus xb squared. Okay, so now we just sort of work the math. We work the algebra here. We're going to multiply this out. Got this squared, and we got this squared. And let me just remind you about something, and for those of you who maybe haven't done algebra for a while or much of it, remember when we have something like this, if we have just, we'll call it a plus b quantity squared, if we have something plus something quantity squared, and we multiply that out, that's equal to a plus b times a plus b. And so you get a times a is a squared plus BA, and then an AB. So I actually get 2 times AB, and then plus the B squared. So if you dredge your mathematical memory, you may remember something like that. We're going to use that. Clearly, we have a sort of an A plus B quantity squared. We've got another A plus B quantity squared, and we'll see where we go with that. So I'll leave that up there for a minute to remind you of that. So let's multiply this out. So we've got a C squared. So from that form, I'm going to have a G squared XB squared plus the 2AB factor. So 2 times that, so plus 2G gamma XB TB. I just sort of moved the terms around in there, which of course we can do. Plus gamma squared TB squared. Okay, so that's what I've got for my first term here. Now let's multiply out this second term, and now we will have to make some more room here. Okay, so this is going to be minus, again, this squared. So I've got m squared xb squared plus 2 times this times that plus 2 m gamma v xb tb m gamma v xb tb. Take it step by step. It looks horrible perhaps, but again, take it step by step and we'll get there. And plus then this thing squared, gamma squared v squared tb squared. Gamma squared vb squared, oops, not vb squared, of course, v squared tb squared. Okay, so that's c squared times this minus this thing squared, and it all equals c squared tb squared minus xb squared there. Now, let's note something here. We've got some things that we can sort of pull together. We've got an xb squared term here. We've got an xb squared term over here. We've got an xb tb term here. With some stuff in front. I've got an xb tb term there. I've got a tb squared and a tb squared term there. So what we're going to do is pull those together, because then we're going to look at this side and compare it to the other side, and we'll actually get some nice results out of that. So let's look at, let's pull all the TB squareds together here. So I've got a C squared, gamma squared, TB squared. So I've got a C squared, gamma squared, TB squared. That's one of my TB squared terms right there. Got another one here. I've got minus gamma squared, V squared, TB squared. Minus gamma squared, V squared, TB squared. And by the way, this is the point where, for those of you who want to practice some algebra here, good place to stop and work through this and see where we end up. So TB squared terms. Now let's look for the XB-TB terms. Okay, so I've got one here. So I've got a C squared. Don't lose the C squared out here. C squared times 2 times G times gamma. So we'll write that as 2G gamma C squared XB TB. That's this term right here. I've got another minus times 2M gamma V XB TB. So I've got minus 2M gamma V XB TB. So that's my XB-TB term here. And then the XB squared terms. I've got one here, and I've got one there. And I think we've got everything correctly here. So we've got C squared times G squared XB squared. So I've got plus C squared times G squared XB squared. And then minus M squared XB squared here. Minus M squared XB squared. There. And I think we got all the terms there. We got 1, 2, 3, 4, 5, 6 terms total. 1, 2, 3, 4, 5, 6. So it looks like we got them all there. Hopefully we didn't make any silly mistakes there. And then still over on this side, I've got C squared tb squared minus xb squared. Okay, here's where the real nice part comes in, because I've got all this over here, okay? And note, actually, let's simplify it, one more step here. And that is, I've got a tb squared term here. I've got tb squared there, so let's pull that out. So this is we're going to write this as c squared gamma squared minus gamma squared v squared times tb squared. And then, same thing here, I've got an xbtb here and an xbtb there, so we'll pull that out and write this as 2g gamma c squared minus 2m gamma v times xb tb. Okay? And then here I've got an xb squared and an xb squared here. So I've got plus c squared g squared minus m squared xb squared equals c squared tb squared minus xb squared. Okay, now here's the nice part. On this side, note we have a tb squared term. Okay, we've got essentially something times tb squared. And then we've got something times xbtb. And then we've got plus something times an xb squared term here. And then on the other side of our equal sign, we've got a c squared tb squared, and then plus really a negative 1 times xb squared, or just minus xb squared there. When you have something of a form like this, if you've got a tb squared here term here, something times tb squared, and over here you have a tb squared, whatever's in front of this tb squared term has to equal this over here. Okay, so what this is telling me is that for this equality to hold on both sides, this thing right here, that right there, has to equal the c squared, because that's what's in front of the tb squared over there. Over here, what's in front of the tb squared is this thing. So this thing equals c squared, and we'll use that in just a minute. Let's look at the xb squared term. Okay, so I've got an xb squared term here. I've got an xb squared term there. What that means for the equality to hold is whatever's in front here, this thing, this coefficient in front of the xb squared term has to equal the coefficient in front of the xb squared term over there, which actually is just negative 1. So I've got a plus this xb squared, and I really have a plus negative 1 xb squared with that minus sign there. So that's another thing I can use. And then finally you say, well, what about this xbtb stuff in the middle here? I don't have any xbtb term over on the right-hand side. What that means is, again, for the equality to hold, is this whole thing here has to be 0. Because I have to have plus 0 times xbtb, because I have essentially 0 times xbtb over there. I don't have any xbtb term, and therefore, whatever this thing is here has to be equal to 0. So let's write our conclusions down here. We'll keep that last part there. Remember, this is our starting point. A lot of algebra here, a fair amount maybe, but the idea is fairly straightforward, we hope. And that is invariant interval equation, which we derived before, our linear form of our two transformation equations with the g and m in there, because we don't know what those are yet. So we just took that, the TA and XA, plugged it in here, and then just cranked through some algebra. And this is where we've gotten to at the moment. So let's see. We just talked through it. We're going to write down the results there. Keep that last line. Okay, so what we've said here from this, we can say, therefore, for those of you who like math, you can do mathematical symbols, therefore. Some of you may know that. So what do we say? Okay, this, the tb squared term, has to equal c squared. So we have c squared gamma squared minus gamma squared v squared equals c squared, the c squared coefficient over there. Let's just work with that a minute. We'll get to the others in a minute. Okay? Well, on this side we have a gamma squared in both terms, so we can do gamma squared times c squared minus v squared equals c squared. So I just pull out the gamma squareds there. And then divide both sides here by the c squared minus v squared. So I get c squared over c squared minus v squared. It should be looking a little familiar to you now. Take the square root of both sides. Everything is positive, so we don't have to worry about it. V is less than c, so this is positive down there, that's positive. So we have gamma equals c over, what am I doing here? So square root of c squared minus v squared. Got lost there a second. Okay, just took the square root of gamma, squared is gamma, square root of c squared is c, square root of c squared minus v squared is square root of c squared minus v squared. And you say, well, you know, what's going on here? Gamma, is that gamma? Really? Well, it is actually. In fact, you can see it a little bit better if before we took the square root, let's do this, because we did this actually in an earlier video clip recently. Let's write this as c squared over c squared 1 minus v squared over c squared, like that. Okay? And, in other words, all I did, c squared minus v squared is the same thing as this, because that's c squared times 1 is c squared. C squared times v squared over c squared is just v squared. That is the same as that. And once I do that, I can cancel the c squareds, and I'm left with 1 over 1 minus v squared over c squared equals gamma squared. Take the square root, and lo and behold, yes, it does equal our familiar Lorentz factor gamma. So the unfortunate part of that is it really didn't tell us anything, except it did tell us that we haven't done anything wrong, at least for this term. If we got something gamma equals something else, where it wasn't our familiar gamma form, then we know, okay, someplace along the line in the algebra or even before that, we had made a mistake. But that confirms that we're on the right track, at least for this term here. So just confirms gamma is 1 over the square root of 1 minus v squared over c squared. So remember, this here is gamma squared. So gamma equals square root of that. So that's the first term. Now let's look at one of the other terms here. So we'll erase this, get some room here. And let's take a look at, let's just do the xb, tb term here. So what this tells us, as we said before, is that this thing inside here, this coefficient has to equal 0 because there's no xb, tb term on the other side. So what that is saying is 2 times g, remember our goal here is to find out what g and m are, 2g gamma c squared minus 2m gamma v has to be equal to 0 for the equality to hold in our original invariant interval equation. We know that's true, at least we derived it. So what do we got here? Well, we have a 2 on each side. We have a gamma on each side, so let's pull that out. So we've got 2 gamma times g c squared minus mv equals 0. And you may remember when we have the product of two things, we've got essentially this times this equals 0. When you have something like that, then in gamma clearly is not 0. Either this has to be 0 or this has to be 0. Since 2 gamma is never equal to 0, right? Therefore, this implies that, gc squared minus mv has to equal 0. And so what that means is, just to do every step here, gc squared, therefore, equals mv. Pull the mv over there, add it to each side. And then from here we get g equals m over, mv over c squared. Okay, so it's maybe a little helpful there. In other words, now we have a little equation involving g and m. If I could find one or the other, then I'd have the other one. So if I had m here, I could find g. If I had g, I could find m. So let's finally look at the last equation here. And we have c squared g squared minus m squared. That's my coefficient for the xb squared term. That has to equal -1. And so let's work with this a minute. And we can write this, in fact, I'd like to get rid of that -1. So that's the same as minus c squared g squared plus m squared equals 1. Or m squared minus c squared g squared equals 1. Just flip those terms there. And so what have we got here? Well, we've got m. Let's write it in terms of m here. So actually, let's come back up here. Get a little more room. So this was our g equation we found here. Let's actually take g and just plug it in here. Is really probably the simplest way to do it. So here's what we've got. We've got m squared minus c squared g squared equals 1. We know from our middle coefficient at equals 0 that this has to be true. So this is m squared minus c squared times mv over c squared, because I got a g squared here, equals 1. And now we're getting someplace, because all we've got left is m and v and c in there. And so just to do the steps here, we've got m squared minus c squared, m squared, v squared over c to the 4th, just squaring everything inside there, equals 1. Looks a little messy, but let's see what we've got here. I've got an m squared and an m squared there. And so we'll, let's put in here. So we've got m squared times 1 minus c squared, v squared over c to the 4th equals 1. And we'll bring it up here to get some more room here. Note, I could have done this already, but no, I've got a c squared here and a c to the 4th there. So the c squared disappears, and that becomes just a c squared down there. So let's write that. We've got m squared times 1, and just to be clear, I had an m squared here and an m squared here, so I pulled out the m squareds, and then I've left with 1. M squared times 1 is m squared. M squared times this term was that term, equals 1 still over here. So what have we got here? I've got m squared, 1 minus v squared over c squared. Well, that looks nice, because I recognize anytime you get something of that form, when you're dealing with special theory of relativity, you say, that looks good, because that looks very close to gamma, right? The form sort of, I can write that in terms of gamma if I wanted to. Equals 1. Okay? Looks even better, because now I can write this as, I can divide each side by this thing. So this equals m squared over 1 minus v squared over c squared. Looking better all the time, because now we take the square root of each side. And that means we get m equals 1 over square root of 1 minus v squared over c squared. And that is gamma, right? 1 over the square root of 1 minus v squared equals c squared. It's gamma. Very nice news there. So now we have everything. M is gamma. So right there, that's gamma. G is just mv over c squared. M is gamma, so G is now gamma v over c squared. G is gamma v over c squared up there. So let's write all that down. So we worked through all this. Remember how we got this again? Invariant interval. We took our two equations that we developed so far, plugged them into the invariant interval equation, worked through the algebra here, and set things equal to each other, worked through some more algebra, and found out that m was simply gamma after all that work, and g was gamma v over c squared. So here's what we have. Oops, I'll erase that. M is this. Just to remind ourselves there. So we have TA, final result here, or we're going to rewrite it in slightly different form. G was gamma V over C squared. So I've got gamma V over C squared times XB plus gamma TB. And XA was M, which is just gamma times XB plus gamma VTB. And those are the Lorentz transformation equations, named after Hendrik Antoon Lorentz, who later on in their careers became sort of a scientific father figure to Einstein. Einstein was younger than Lorentz, as we mentioned before. Lorentz really extended Maxwell's theory of electromagnetism during the 1890s and into the beginning of the 1900s, and working with Henri Poincaré as well. Very sophisticated theory, and he had come up with these equations in the context of that theory. Einstein came up with them, as we've seen, just from his two basic postulates involving essentially clocks and lengths, and so it was coming to them from a very different perspective. Although many people at first thought, Einstein, you're just rederiving what we already know here from Lorentz and Poincaré as well, these Lorentz transformation equations. But because Einstein was coming from such a different perspective, they were renamed, certainly for a while, the Lorentz-Einstein transformation equations. And then as time went on, people realized that Einstein's approach really was the more fundamental approach to the matter, and yet still we call them Lorentz transformations to honor Lorentz's contributions to this. And Einstein himself looked up to Lorentz a great deal. So here are the two equations. We want to rewrite them in slightly different form just to make it easier to remember, and also to bring out the difference and similarities to the Galilean transformation. So I'm going to rewrite this as TA equals, note I've got a gamma in each term there. So I'm going to pull out the gamma. I'm going to put the TB term first. TB plus V over C squared XB. Okay, so I flipped the terms. I put the TB term first, and I pulled out the gamma factor. And then XA is, again, I can pull out the gamma here. So gamma XB plus VTB there. So first of all, especially the XA term here, well, first of all, just these two equations, if you look at them, they both have gamma in front of them. Okay, that indicates special theory of relativity is going on here. And the form is similar. You know, I've got an XB term plus a TB term. And for the TA, I wrote the TB term first because you've got the TB and XB, and the second terms have the extra coefficient in front of them. For the XA equation here, it's V times TB because the units have to match. V is meters per second, for example. Length divided by time. This is time, so this gives us units of length, for example, meters. Here, it's the equation for time, and velocity is meters per second. We'll use the meters in second system, MKS system as it's known. C squared is a velocity squared. Okay, so that's going to give me, if I have a velocity here and a velocity squared down here, I get a velocity in the denominator, and I've got meters here, a length. And so if you do the cancellation there, you get essentially a time factor, seconds in terms of the units there, and it all works out. Gamma, of course, being dimensionless. Right? So the units check out. If they didn't check out, we would have made a mistake someplace along the way. So that's the general form. And this is probably a nice form to memorize them in if you're going to be using them fairly frequently, and we'll certainly be referring to them as we go on throughout the course.